Hello everyone and welcome to Lecture Today. In today's lecture, what we're going to be doing is generalizing the idea of convergence to series with non-positive terms, possibly containing non-positive terms. So up until now, all of the series that we've discussed, and specifically the convergence test that we've discussed, have required that the infinite series be composed of terms ak, so a1 plus a2 plus a3 all the way up to infinity, such that all of the ak's are positive or equal to 0. This is the test that we've discussed so far. Have been the direct comparison theorem, the limit comparison theorem, and the integral test. But we know that this is not in general the case. Right? In general, we can have a series with both positive and negative terms, and there is going to be a special type of convergence that we're going to have to define for such series. So to give you an example, right, if you take a geometric series, we'll just take a simple geometric series, negative 1 over 2 to the k, for k from 0 to infinity. This is going to be negative 1/2 to the 0, which is just 1 minus 1/2 plus negative 1/2 squared, which is going to be positive 1/4. Then it'll be minus 1 over 2 cubed, and so on and so forth all the way to infinity. So this is an example from talking about a series of negative terms. This is specifically a geometric series with r between negative 1 and 0. So we know that this series converges. It converges very nicely to 1 over 1 minus negative 1/2, or 2/3. This is an example of a series with negative terms that is convergent. For another example of a series with negative terms that is convergent, we can look at what's called the alternating harmonic series. And this is, as you might expect, related to the classical harmonic series. Specifically, it has the formula of summation from k equals 1 to infinity of negative 1 to the k minus 1 over k, which when we write this out is going to become negative 1 to the 0, which is 1 over 1. This is going to be 1. Then it'll be negative 1 to the 2 minus 1, so negative 1 to the 1, which is negative 1 over 2, plus 1 over 3 minus 1 over 4, plus 1 over 5th, and so on and so forth. Now, unlike the harmonic series, which diverges, it can be shown that the alternating harmonic series converges to a specific number, the natural log of 2. I'm not going to go over how to show this right now. I'll talk about it a little bit in the next lecture. I just want to use this as an example of the defining the two types of convergence we're going to define in this lecture right here. So the point here is that both of these two series are series that contain negative terms and converge. So in lieu of a proof of this, I just want to kind of convince you that this alternating series does in fact converge. So what I did was I just kind of took the sequence plotter code from before and altered it a little bit to plot out the sequence of partial sums of this series. So the first n terms of this infinite series to show that the sequence of partial sums is in fact getting closer and closer and closer to ln of 2. So this line right here is ln of 2, and if I show the sequence of partial sums, so the first partial sum of the sequence is just 1. The next partial sum, so that means that the second partial sum is 1 plus negative 1/2, which is positive 1/2. The third term is going to be .833333 because it's going to be 1 plus negative 1/2 plus 1/3, and so on and so forth, all the way to infinity. So remember, this purple line right here is natural log of 2. If we look at what this sequence of partial sums is doing, it's getting closer and closer and closer to this line, natural log of 2. So this is why the infinite series converges just from a graphical perspective. It's not a direct mathematical proof, but it's, I think, should be good enough justification for now to show what I'm talking about. So despite the fact that both of these series are convergent series with negative and positive terms in them, they have a fundamental difference to them. And the fundamental difference is, can be observed directly when we look at what's called the absolute form of these series. And that's the sum of the absolute values of the terms in these series. So for the geometric example, we look at the sum from k equals 0 to infinity of the absolute value of negative 1/2 to the k. Well, this is going to be the same thing as the sum from k equals 0 to infinity of just 1/2 to the power k, which is 1 plus 1/2 plus 1/4 plus 1 over 2 cubed, and so on and so forth, which we recognize as a convergent geometric series. Specifically, this converges to 1 over 1 minus 1/2, which is equal to 2. So what we say then is that in general, if you take a general series with positive and negative terms, if the sum of its absolute values is convergent, this is how we define what's called an absolutely convergent series. And this is how we're going to define absolutely convergent. And the idea here is that an absolutely convergent series is in some sense much nicer than what's called a conditionally convergent series. If you look down to this alternating harmonic series example, you know that if you look at the absolute form of this series, the sum from 1 to infinity of the absolute value of negative 1 to the k minus 1 over k, this is just the sum from k equals 1 to infinity of 1 over k, or 1 plus 1/2 plus 1/3 plus 1/4, and so on and so forth, which we recognize as a p-series with p equal to 1, or our standard harmonic series, which diverges because p is equal to 1. So this is a good example of what's called a conditionally convergent series. And in some sense, we have to be very, very careful with conditionally convergent series, as I will talk about in the next lecture video. But for this lecture video, we're really only going to be considering absolutely convergent series, in some sense how an absolutely convergent series relates to conditionally convergent series. We'll get into the details of conditionally convergent series in the next lecture. So to write down a definition of this, we say that absolutely convergent is defined in the following way. We say that a series of AKs converges absolutely, or is absolutely convergent, if the corresponding series of absolute values converges. We also have that a series converges conditionally if it is not absolutely convergent, so the sum of the absolute values diverges, but it is convergent. So these are the two main definitions that we have. And in this lecture, we're going to focus on absolutely convergent series and some basic tests that we have for showing absolute convergence, because this is going to be a very important property going forward. For an abbreviation, sometimes I will write A dot C if a series is absolutely convergent, or C dot C if a series is conditionally convergent. But an important thing to note here, and something that I think confuses a lot of students initially, is that a series is either absolutely convergent or conditionally convergent. It can never have both properties. Okay? And this is an important thing to point out about these two definitions. So we have one very nice relationship between the series, and this is sometimes called the absolute convergence test, the absolute convergence theorem. We have that if a given infinite series of absolute values converges, then the series itself, the original series itself, must also converge. And I'll write a proof sketch here just to kind of go through and show you how to see this. You know that the series is always going to be bounded above and below by positive times the absolute value, positive 1 times the absolute value of AK, and negative times the absolute value of AK. So because of this inequality, we can add absolute value of AK to both sides to get that 0 has to be less than or equal to AK plus the absolute value of AK, which has to be less than or equal to absolute value of AK plus absolute value of AK, which is 2 times the absolute value of AK. And then from the direct comparison theorem, we can say that, well, because by assumption, the sum of the absolute value of AK's converge, the sum of the 2 times the absolute value of AK's must also converge. So because this converges, the sum of infinite series of AK plus the absolute value of AK must also converge. By the DCT, and this can then be used to directly show that the sum of the AKs itself must converge. Now, we don't necessarily know the value this converges to, but we do know that this is going to be true, and the details can be found in the book. But the point is that this is a very, very nice theorem, because essentially what we have is that if we can show that a given series with positive and negative terms in it is absolutely convergent, then or the absolute values, the sum of all the absolute values converges, then the series must also converge. We don't necessarily know what the value it converges to, but if we can show that the sum of the absolute values converges, then the series must also be convergent. So this is a super useful theorem for that reason. And the usefulness here stems from the fact that we have 2 very, very nice tests that will tell us very often, they're very, very useful and very, I'd say, relatively straightforward to apply to test whether or not a series is absolutely convergent or not. So these 2 tests are called the ratio test and the root test, and are the 2 tests that we're going to consider in this lecture. So what I'll start by doing is giving a motivation for the ratio test, and then I will write it down. And the main idea here is that for a general series of AKs, the ratio test can be thought of as comparing that series of AKs, the general series, to a geometric series. And recall, take a general geometric series. I'll just call the terms BK. Geometric series are defined by the following fact that the terms in the series or I should say the subsequent terms in the series all share a common ratio, R. So this is B1, this is B2, this is B3, this is B4, and so on and so forth. And actually, let's make this a little bit nicer by putting the correct indices in here. So there should be B0, B1, B2, and B3. But what we notice is that if I look at the ratio of terms in the geometric series, B1 divided by B0 is this divided by this, which is just R. B2 over B1 is also equal to R. B3 over B2 is equal to R. And so the limit as k goes to infinity of bk plus 1 over bk in absolute value is just going to be equal to the absolute value of r for the geometric series. And we know that when this is strictly less than 1, the series converges. And if it's greater than or equal to 1, the series diverges. This is for the geometric series, remember. This is kind of like a review. And the idea behind the ratio test now is for a general non-geometric series, what we're going to be doing is looking at the limit as k goes to infinity of the ratio, the absolute value of the ratio of subsequent terms in the series. And we'll call this limit rho. And the idea here now is that this value of rho is essentially, in some sense, telling us that how kind of closely this general series of AKs is related to a geometric series with rho as the r value. This is a good way of kind of thinking about this idea and this theorem. So looking at the ratio of subsequent terms in the series, or the absolute value of the ratio of subsequent terms in the series as k gets larger and larger and larger, is essentially giving us an idea of how closely this series is resembling a geometric series, or what type of geometric series this is resembling as k gets larger and larger and larger. And this is the general reason now that when we write down the ratio test, the ratio test is stated as follows. That we call the limit as k goes to infinity of the absolute value of ak plus 1 over ak. This limit we're going to call rho. This is for a given infinite series of AKs. So if this is the case, then we have the following results of the ratio test. The first one is that if rho is less than 1, then the series converges absolutely, or is absolutely convergent. If rho is strictly greater than 1, then the series diverges. In the last possible scenario right here is that if rho is equal to 1, then the ratio test is inconclusive, which basically means that we don't know. It's not working. We don't know if the series converges or diverges. We have to choose a different test to use to test for absolute convergence. So of the three possibilities, the third possibility is the worst possibility, because it means you have to do another test, that the ratio test is not going to give you any results at all. But for the first two possibilities, you get a very strong result. You get that if rho is less than 1, then the series is absolutely convergent, because for large values of k, it's essentially looking like a geometric series with an r value of less than 1. And if rho is greater than 1, then we can conclude this exact same thing. Then the series is going to diverge because this is acting like a geometric series with an R value that's greater than 1. So what I want to do is go over an example right now. And this example is just going to be a relatively straightforward example of applying this ratio test to show convergence or divergence. And this is going to be the sum from n equals 1 to infinity of negative 1 to the n times n plus 2 over 3 to the power n. And essentially, the first term of this sum is going to be negative 1, because it'll be negative 1 to the 1 times 1 plus 2 over 3 to the 1. Which will be negative 1 times 3 over 3, or just negative 1. The next term will be 4/9. And this is because we have negative 1 squared is positive 1, and then 2 plus 2 is 4, divided by 3 to the power 2 is 9. So then for the same method, third term is negative 5 over 3 cubed, and this is going to continue onwards to infinity. So the whole idea here is we need to figure out exactly, using the ratio test, whether or not this series converges or not. Absolutely. Or if we can't use the ratio test at all. So to that end, we're going to look at the limit as k goes to infinity of ak plus 1 over ak. For the k plus 1 first term over a kth term, and see where that goes. And I just realized here that I should be using n here because that's the index of summation that I use above, and I think that'll be a little bit nicer to write down. So we have a look at the limit as n goes to infinity of an plus 1 over an, and see where this gets us. This is just taking the n plus first term of the sequence or the series and dividing by the nth term of the series. So this limit as n goes to infinity is going to be negative 1 to the n plus 1 times n plus 1 plus 2 divided by 3 to the power n plus 1. And this will be divided by negative 1 to the n times n plus 1 over 3 to the n. N plus 2. And at first this looks a little bit intimidating, but it's not that bad, especially if we remember how absolute values work. If you take the absolute value of a times b over c times d, this is the same thing as the absolute value of a times the absolute value of b over the absolute value of c times the absolute value of d. And what that means then is that we can take the absolute value of each one of these terms individually, and negative 1 to the n plus 1 and negative 1 to the n terms are going to end up going away, because the absolute value of any negative number, or specifically the absolute value of negative 1, if negative 1 to the n is negative 1, the absolute value of that will be 1. So these things end up going away directly because of that. And we can use some arithmetic to simplify the rest. This will be n plus 3 over n plus 2 times 3 to the power n over 3 to the n plus 1. Which can be simplified even further by taking a look at our limit law. So what we have for our limit law. And you'll remember that if we have two separate sequences and the limit of both of them exists from Calc 1, the limit of the result is going to be the multiplication of these two limits. So the limit that we're looking for is going to be the limit of n plus 3 over n plus 2 times the limit of 3 to the n over 3 to the n plus 1, which is 3 to the n times 3 in the denominator there. So the idea here then is that this first limit goes to 1 by L'Hopital's rule. It's a very nice, quick L'Hopital's rule calculation. And then the second limit simplifies even more because we have 3 to the n divided by 3 to the n, which cancels out, which means this second limit is going to be 1/3. So the entire limit here is 1/3, which is our rho, and this value is less than 1, strictly less than 1. And therefore, we say that by the ratio test, the series that we started with is absolutely convergent, which means that the sum of the absolute values of this series converges, which in turn means that the series itself converges as well. So this is pretty cool. Let's do one more, we'll probably do a couple more examples of this just to really get the idea down. So we'll do the sum from n equals 0 to infinity of 2 to the n over n factorial. And what I want to do is do a quick little review of n factorial. Remember, this is the function on the integers, or on the natural numbers, such that for every n factorial is the integer n multiplied by n minus 1 factorial. So this is called the recursive definition, with 0 factorial equal to 1. This means that then 1 factorial is going to be equal to 1 times 0 factorial, which is equal to 1. 2 factorial is going to be equal to 2 times 1 factorial, which is 2. 3 factorial is going to be equal to 3 times 2 factorial, which is 3 times 2. And so on and so forth, all the way down to n factorial, being equal to n times n minus 1 factorial, which essentially what it ends up being is 1 times 2 times 3, all the way up to n. That's the multiplication of the first n integers. This is how we define the factorial function on the integers, and it's a very, very important function. I mentioned it earlier in terms of limits of sequences, but this is going to be super important to us when we go through and do Taylor series. This is just kind of like a little review of this to kind of understand this. Another interesting thing is that the factorial function grows really, really, really fast. Super, super, super fast. It's so fast it's really hard to describe sometimes, hard to understand for most people. But to give you an idea, Elon Musk is currently worth around $125 billion, and it would take him 13 days to go broke or 14 days to go broke if he were to pay you n factorial dollars each day you work for him. So 1 factorial on the first day, 2 factorial dollars on the second day, 3 factorial dollars on the third day, and so on and so forth. It would take him 14 days to go broke if he were to pay you at this rate, which is just a quick example to show how fast this function is growing. So for the ratio test, we're always considering the limit as n goes to infinity of the absolute value of an plus 1 over an. And this is going to be the same thing as the limit as n goes to infinity of 2 to the n plus 1 over n plus 1 factorial. And this is going to be over 2 to the n over n factorial, which we can directly use some arithmetic to simplify, and this becomes the limit as n goes to infinity of 2 to the n plus 1 over 2 to the n times n factorial over n plus 1 factorial. Which will simplify nicely using our limit law, our product limit law from before. This will be the limit as n goes to infinity of 2 to the n times 2 over 2 to the n. And this is going to be multiplied by the limit as n goes to infinity of n factorial over n plus 1 times n factorial. And this is by the definition of the factorial function. And for both of these, we get some nice cancellations. For the first one, 2 to the n divided by 2 to the n cancels out, just 1. And n factorial over n factorial also cancels out. So this first limit is going to be 2, and the second limit is going to be the limit of 1 over n plus 1 as n goes to infinity, which is 0. So our rho value for this ratio test is 0, which is less than 1. And therefore we conclude that by the ratio test, this series that we start with converges absolutely. Which is very cool. And I also want to point out that there were no negative terms in this series, but this also means that if we were to add negative terms into the series, it would change the series. But any series that is close to this one right here, say, for example, the series from 1 or from 0 to infinity of negative 1 to the n times 2 to the n over n factorial, this series will also converge absolutely, because when we take the absolute values into the ratio test on it, we'll get the same limit as before. So I wanted to just kind of point that out, that this is a very, very, very powerful test. For the next example, we'll consider the series for n from 2 to infinity of 3 to the n plus 2 over natural log of n. So we gotta look at the limit as n goes to infinity of 3 to the n plus 1 plus 2 over the natural log of n plus 1 over 3 to the n plus 2 over the natural log of n. Because this is, there are terms an, and this is an plus 1, and this is an. Realistically, it's the absolute value of this, but it doesn't really matter too much here because we don't have any negative terms or not. But it's good to get in the practice of taking the absolute value of this limit, because this is what you got to deal with in general. This is the same thing as the limit as n goes to infinity of 3 to the n plus 3 over 3 to the n plus 2 times the natural log of n over the natural log of n plus 1 . And so this is going to be the same thing as the limit as n goes to infinity of 3 to the n times 3 cubed over 3 to the n times 3 squared times the limit as n goes to infinity of the natural log of n over the natural log of n plus 1. And after one application of L'Hopital's rule, actually two applications of L'Hopital's rule, you see that this limit goes to 1. And for this limit, we have a cancellation here. The 3 to the n over 3 to the n cancels. And then 3 cubed over 3 squared is just equal to 3. So this limit is equal to 3, which means the rho value for this ratio test is strictly greater than 1, and therefore this series, this infinite series, diverges. According to the ratio test. The reasoning behind this, again, is that essentially this rho measurement is saying that this series for large values of n is acting like a geometric series with an r value that's greater than 1, and therefore this series diverges. So this is a good example of part 2 of this theorem. So we've seen a couple different examples of part 1, a couple of different examples of part 2, and for the last example I go over, I really want to make a point to emphasize, right, the inconclusive part in this next example. So in order to do this, I'm going to use two relatively simple series. I'm going to use the harmonic series, and I'm going to use the p series. And I'll kind of do the ratio test on both of these. And I'm going to see what the ratio test is telling us. The limit, as n goes to infinity, of the harmonic series is going to be 1 over k plus 1 over 1 over k as k goes to infinity. And this ratio, after simplifying and doing L'Hopital's rule, ends up being 1. And what this means for the harmonic series is that the ratio test is inconclusive for this example, for the harmonic series. So basically what this is saying is that we cannot use the ratio test to determine the convergence or divergence of this series. Of course, we know from our integral test and previous examples, right, that the harmonic series diverges, the divergent series, but we cannot use the ratio test to show this because of this inconclusivity result from the ratio test. So this happens whenever the limit is equal to 1. This happens as well for this example right here. It's going to be 1 over k plus 1 squared over 1 over k squared. And after a couple applications of L'Hopital's rule, after we simplify this, we get that this limit is also equal to 1, which corresponds to outcome 3 of the ratio test. So even for the p series with p equals 2, the ratio test is inconclusive. Of course, we know that this series converges because it's a p series, p greater than 1, but we cannot use the ratio test to show this. So whenever you do the ratio test and you get a limit of 1, you have to use some other test to investigate the convergence or divergence. And this will happen actually for you for all p series, as well as many other different possible series. So this is kind of, I think, a good summary of the ratio test and a number of different examples of that. So it's a very, very powerful test, but it does have its limitations, which is why we need multiple tests here to test convergence or divergence of series. The next test that we're going to go over is called the root test, which is a similar idea to the ratio test, but it's a little bit more involved. But it's the same idea. We're going to investigate a specific limit, and that limit is going to tell us how close our complicated series is acting to a geometric series.